Thank you very much for inviting me to give this lesson at the MEFI, for the MEFI students. I am a professor at the University of Bordeaux, and I am also foreign professor at MEFI. And the goal of this presentation will be to give you an introduction on inertial confinement fusion. So now I will share my screen and I will put on my presentation. Just tell me if you see it. I will start by making some history, okay? The history of nuclear fusion started about 80 years ago in United States and in the Soviet Union. The names which are related to nuclear fusion are names like Sakharov in the Soviet Union and Teller in the United States. And actually, if you know, these are the same names which in a way are related to development of the hydrogen bomb, because hydrogen bomb is related to, is working on the basis of nuclear fusion. So after developing the hydrogen bomb, these scientists thought that it could also be possible to use nuclear fusion in a controlled way for the production of energy. And actually, they thought that it was quite easy, because they said, this was in the 50s, they said maybe in 20, 30 years, we will have power plants working on nuclear fusion. And indeed, this task has proved to be much more difficult than they thought at the beginning. Then, 60 years ago, the laser was invented. And soon after, other scientists thought that it was possible to use laser to achieve nuclear fusion. And this is what is called inertial confinement fusion. And the names are, again, Bazov, who is a Russian scientist who got the Nobel Prize for the invention of the laser in the Soviet Union, and scientists like Nichols in the United States, who again were inspired by the work of Teller. Now, today, we are still facing big difficulties in achieving nuclear fusion, but I believe that we are close to the demonstration of ignition, which is the scientific feasibility of fusion on Earth, which will conclude the first part of this travel. Of course, once we have demonstrated ignition, we will still have to do a lot of work, both in physics and in engineering, to realize power plants which are based on fusion. But at least we will know that it is possible to make fusion on Earth. So this is what the outline of my talk. I will first present what is nuclear fusion. Then I will speak briefly about nuclear fusion in stars. Then how we can make nuclear fusion on Earth, and how we can think about new energy sources based on fusion. And I will speak about inertial fusion and the big laser installation, which today can be used to demonstrate ignition of thermonuclear targets. These are, at the moment, the National Ignition Facility in the USA, which is fully operating. The laser megajoule LMJ in France, which is still in a construction phase. And then Shenzhen laser in China. And then there are other projects for building other lasers, including in Russia. So let me just start very, very simple. I mean, most of you know everything here. Just take it as a reminder. So if we look at the nucleus of the atom, we know that there are protons and neutrons. And protons have electrical charge, and because they are all positive, they tend to repel each other. So the Coulomb force tries to break the nucleus. So the nucleus is kept together because in addition to the electrical force, you have the nuclear force, which attracts protons among them, it attracts neutrons among them, it attracts proton to neutron. So neutrons are not involved in the Coulomb force because the electrical charge is 0. So the nucleus is stable thanks to the nuclear force, and because the neutrons do not have a charge, they have a stabilizing effect on the nucleus. Now, the nuclear force is stronger than the electromagnetic force, but it is short range. The electric force is weaker, but it is long range. This means that if you have two different nuclei and you put them at short distance, by short distance, I mean really they must touch each other. The distance must be of the order of the dimension of the atomic nucleus. Then the nuclear force win, and they will attract strongly each other. But as soon as you separate them a bit more, the electrical repulsion wins because it is longer distance, and they will repel each other. So when you bring in contact these nuclei, they can undergo a fusion reaction to give a bigger nucleus. And some of these nuclear fusion reactions may release a big amount of energy. I show this graph where in X you have the number of nucleons in the nucleus, that is the total number of particles, protons plus neutrons. And in Y you have the average nucleon bonding energy. So this is the energy which you need, which you get from extracting one, you need to provide to extract one nucleon from the nucleon. On the right, you see the picture of von Weizsäcker, who was a German scientist who studied this curve. And indeed, yes, there is a formula which is called Weizsäcker formula, which can reproduce the behavior of this binding energy. Now, if we look at heavy nuclei, like uranium-238, uranium-235, and we, by some means, we are able to break them, we can get this difference in energy as free energy. So heavy elements release energy by nuclear fission. That is when they are broken in smaller elements. On the contrary, if you can get light nucleus and merge them together, if you can make nuclear fusion, again, you gain energy. Light elements release energy by nuclear fusion. Yeah, that is when they make larger nuclei. And if you compare this graph with the previous graph, you see that the energy which is released by nuclear fusion is much bigger than the energy which is released by nuclear fission. This is one reason why we are interested in nuclear fusion. But of course, there are two other reasons which are maybe even more important. The first reason is that the fuel for nuclear fusion is hydrogen or deuterium, which is an isotope of hydrogen, which is very, very abundant on Earth. There is much more deuterium contained in the seawater than all the uranium existing on Earth. So it means that the fuel can be sufficient for centuries. And the second reason is that, of course, as you know, when you break uranium and you make nuclear fission, you have radioactive waste. And this problem is much less important with nuclear fusion. Finally, there is some other point which is important in this curve. That is, you see there is a maximum and the maximum is around iron. And these elements in nature are very stable because you do not release energy when you break them to make fission, and you do not release energy when you fuse them to make fusion. So both fission and in order to do fission and fusion for this element, you have to provide energy. They never give useful energy. So it means that in normal condition, they are very stable. Well, where does the release the energy coming from? Actually, it's coming from a difference of mass. If you make the fusion between deuterium and tritium, which are two isotopes of hydrogen, in the end, you will get helium and a neutron, and the mass of these final particles is less than the mass of the initial particles. And the difference of mass is related to the released energy by using well-known Einstein formula. Okay, so this is nuclear fusion, and nuclear fusion is the source of energy in the stars. The energy which makes the stars to release continuously energy, which we receive as illumination from the sun, for instance, is coming from nuclear fusion reaction taking place into these stars. Actually, this was not understood until the 30s. Before, the people didn't know what was the origin of the energy in the stars. There were some ideas, maybe somebody was thinking that it was indeed related to nuclear fission. But in 1939, the German physicist Hans Bethe, who is also a Nobel Prize for Physics, proposed the chain of nuclear reaction which brings to the energy production in hot stars. And this theory is important because it explains the origin of the energy production in the stars, but also because it explains the formation of the elements in the universe. You know that after Big Bang, the only element which was existing was hydrogen, and then because of nuclear fusion, you could get all the heavier elements. So this is the chain of nuclear fusion reaction, which works in the stars like the sun. The sun is just a small star. For the bigger stars, there are more complex fusion reactions, but now it's not very interesting for us. Now, you see, in the stars, in the star like the sun, you start from hydrogen atoms. You get fusion of 2 hydrogen to get 1 deuterium. This deuterium has a nuclear fusion with an additional hydrogen to make helium-3. And from the fusion of 2 helium-3 nuclei, you get 1 helium-4 plus additional hydrogen. So, in conclusion, let's say the star is using hydrogen as a fuel to produce helium. And in this chain, at every fusion, you gain some energy. Well, actually, this tells us many information about how the stars are working. The stars are systems in dynamical equilibrium. On one side, you have the gravitational force, which tends to make the star to collapse. It tends to implode the stars. And this gravitational force is counterbalanced by the energy which is released by the nuclear fusion reaction taking place in the core of the star. This is, in the end, is what brings to radiation pressure, and this pressure from the generated radiation counterbalance the gravitational force. So what is happening during the life of a star? At the beginning, the star is burning hydrogen and it produces helium. When hydrogen becomes less abundant, the star begins to be a star which is made mainly of helium. And then the nuclear fusion reaction decreases in number. So the radiation pressure decreases. And this means that the gravitational force is winning. So the stars will contract. It will become smaller, more dense, and the temperature will increase. And in the new condition of temperature and density, you can get the fusion of helium. So helium will begin to make fusion to produce carbon and oxygen. And this cycle will repeat many times. When helium is going to finish, the star will contract again, the density and the temperature will increase, and then you will begin to get fusion of carbon and oxygen. And this will produce heavier elements like sulfur and silicon. And then, at a given time, this cycle will finish because you will finally produce nucleus which are iron or elements which are very close to iron. And at this point, the fusion of iron will not provide additional energy. It will not provide radiation pressure, but on the contrary, it will consume energy. So what happens at this stage? When the star has come to the point of producing iron, the radiation pressure is not enough to win the gravitational force, and the star will collapse. And because of this collapse, which will be very, very fast, then there will be a following rebound, there will be an explosion, which is a supernova explosion. So in this view graph, you see the structure of a big star before the supernova explosion. Okay, you see in the outer layer, you will get still light elements, but then when you go to the center, you will find heavier and heavier elements. And when the number of iron atoms in the star becomes too big, then the engine, the motor of this star, which is the nuclear fusion, will stop working, and the gravitational force will win, and you will get the supernova explosion. And you see, the processes are very fast. If you get a big star, in order to, in the beginning, it will burn hydrogen, and this will need a temperature of 40 million degrees, and you will need a very high density. And this phase can last for millions of years. And then the star will begin to burn helium, and this is 500,000 years. And then it will start to burn carbon and oxygen, and you see, this is very fast. And then it will start to fuse silicium to produce iron, and this will be only one day. And after this, you will get the supernova explosion. Well, all these depends on the size of the star. Okay, this is the Crab Nebula, which was formed by the supernova explosion of 1000 over 1054. This is a supernova explosion, which is well known because it was recorded by the Chinese astronomer at the time. So, what happens after the for a very big star? You will get all the history which I just told you. If the star is not so big, the history will be, sorry, if the star is not so big, they will be a bit different. Because for a star like the sun, when it contracts, the temperature may be not sufficient to trigger the fusion or heavy element like carbon and oxygen. So at this point, the star will contract without going to the phase of a supernova explosion, and it will become what is called a white dwarf star, which is rich in carbon and oxygen. And there are thousands of these white dwarfs in the universe. So this is just a summary of what happens to the stars depending on the mass. Well, if you have a very small mass, which is about 7% of the mass of the sun, the temperature in the center will never be enough to trigger hydrogen fusion. So this object will be an aborted star, what is called a brown dwarf. It's like a much bigger Jupiter, let's say. If you have the stars which have a mass between 7% of the sun and 8 times the mass of the sun, these are the small stars which burn hydrogen and helium. But after they burn helium, they are not able to burn carbon. And this star becomes a white dwarf of carbon and oxygen. If you have bigger stars, then they will burn carbon, oxygen, they will become a red supergiant, and finally, as I was telling you before, the star will explode like a supernova. And then, depending on the mass of the star, again, if the mass is below 25 times the mass of the star, the residual of the supernova will become a neutron stars. And if it is bigger, in the end, it will become a black hole. Now, let's go back to nuclear fusion on Earth. So we have seen that nuclear fusion in stars is very complex chain. This one, the Bethe chain is very, very difficult because it involves many steps, and it starts from hydrogen to finally get helium. Now, we are not able, and we will never be able, to produce energy on Earth using the same chain. We have to rely on something simpler. And actually, we use the isotope of hydrogen. We use deuterium, which is the hydrogen with 1 proton and 1 neutron. And we use tritium, one proton and 2 neutrons. Why we use this one? Because this is a single-step nuclear fusion, okay? You see, you get deuterium, you get tritium, you fuse them, you get a nucleus of helium-5, which is very unstable, and which breaks immediately into a nucleus of helium, a so-called alpha particles, and in a neutron. And in this process, 17.6 megaelectron volt of free energy are released. And is a graph of the cross-section of the reaction as a function of the energy of the particle. So you see that if you compare the deuterium-tritium to other nuclear fusion reaction, this is characterized by having a bigger cross-section, which means the reaction is more probable, and by having a peak at lower energies. Of course, we were telling before that the electrical force is long range. So if you have deuterium and deuterium, or if you have deuterium and tritium, you have to accelerate these nuclei at very high velocity in order that they are able to get close enough to each other to have nuclear fusion. So very high velocity means very high energy, means very high temperature. So the fact that this peak for deuterium-tritium is at much lower energy than, for instance, this reaction, deuterium-helium-3, or the reaction deuterium-deuterium, means that it is easier to be produced in the laboratory. So we were saying just now that in order to touch each other, the two nuclei must have a high velocity in order to win Coulomb repulsion. And of course, from the point of view of statistical physics, high velocity means high temperature. And actually, in order to get a fusion reaction between deuterium and tritium, you must have this mixture of deuterium and tritium at very high temperature, between 5 and 10 kV. Now, which is 5,000 to 10,000 electron volt. And 1 electron volt is 10,000 Kelvin. So 10 kV means 10 million degrees. So actually, we are speaking about huge temperatures, actually the temperatures which are comparable to what you can find in the stars. And of course, at such high temperatures, the hydrogen atoms are fully ionized and matter become a plasma. That is a mixture of neutron, ions, and electrons. So the first condition to get nuclear fusion on Earth is that I must take deuterium and tritium, the nuclear fuel, and heat up to this enormous temperature. But actually this is not sufficient, because in order to get a large production of energy, you need many fusion reactions, which means that you must keep the ions together for a long time, for a long enough time. This is called confinement time. And this is bringing to what is called as Lawson criterion, which tells that if you want to get a gain of energy out of this deuterium-tritium plasma, you have to satisfy this formula, that is the product of the electron density, which is the same as ion density because we are in the case of hydrogen, times the confinement time tau must be at least 1.5 10 to the 14 second per cubic centimeter. Now, if we want to, there are different ways in which we can satisfy the Lawson criterion. Okay, this is just the summary of this. We can, if we want to satisfy this Lawson criterion, we can have a big density of the plasma and shorter confinement time, Or, on the contrary, we can have lower density and very big confinement time. And this brings to two different pathways to try to achieve nuclear fusion. You have magnetic confinement fusion, in which a low-density plasma is confined by a strong magnetic field. Because of the magnetic field, the particles cannot go away. They are bound to move along the thin lines, the field lines, and so they are confined for a long time. So in the case of magnetic confinement fusion, you satisfy the Lawson criterion because you have a low density but very long confinement times. And then you can have inertial confinement fusion, the fusion by laser, in which, on the contrary, you use the laser to get compression of matter, so you get very high density, but the confinement time is very, very small. And then you have gravitational confinement, which is working in star. And this is much more efficient because in this case you have very high density and you have very long confinement time. The confinement time is the lifetime of the star, so it's practically infinite compared to the nuclear fusion reaction. But unfortunately, as we said, we are not able on Earth to get at the same time high density and long confinement time. We can just try to get long confinement time or high densities. And then, of course, there is another way to achieve nuclear fusion, which is what has been used in the hydrogen bomb. And in this case, you use a conventional nuclear bomb, which is realized with uranium or with plutonium, to compress the thermonuclear fuel, the mixture of deuterium and tritium. And then, in this case, you can compress quite a big mass of deuterium and tritium for times which are long enough, let's say of the order of microsecond. Now, actually, this comparison tells us something. It tells that if we want nuclear fusion for the production of energy, if we want controlled nuclear fusion, we need to ignite, of course, using different tools, not a uranium bomb. We need to ignite using, for instance, lasers. But also we need to ignite a small mass of the fuel, because if the mass of the fuel is big, even if we ignite with laser, in the end we will get a big explosion. Now, this is an example of a tokamak system. This is the scheme of the JET, the Joint European Torus, which is a European project which is installed in Calais in the United Kingdom. It is the bigger tokamak which is working today. Actually, the tokamak is a particular configuration of the magnetic field which was invented in the Soviet Union and which today is thought to be the best approach to magnetic confinement fusion. And you can see the dimension of the jet by comparing with the man inside the vacuum chamber. I mean, when there is no vacuum, of course. The next step for the magnetic confinement fusion is the so-called ITER project. ITER stands for International Thermonuclear Experimental Reactor, which is a collaboration between the European Union, United States, India, Korea, China, Japan, and Russia. The cost of this machine is enormous. The size of the machine is enormous, and the construction should be finished by 2025, probably. The ITER project, the ITER machine is under construction in Cadarache, which is in the south of France, near Marseille. And actually, the original idea of this project was following the meeting between Gorbachev and Reagan in November 1985 in Geneva, in Switzerland. This was a meeting in which they were discussing about control of atomic weapon, and also idea of an international tokamak to demonstrate nuclear fusion. Is everything okay until here? Maybe somebody wants to make question now, or I should go on? Irina, should I go on, or I go on, or you want to make, somebody wants to make question, or I go on?
No, the question maybe at the end of your lecture.
Okay, so I go on. So now let's speak about inertial confinement fusion. How does it work? Well, the idea is that you take some deuterium and tritium in the form of DT ice. So this is a frozen deuterium tritium, because you want to start with the high density and you want to compress it to get a bigger, even bigger density. And then this sphere, you shine with the lasers. The irradiation creates ablation. I mean, the surface layer of this sphere is changed into a hot plasma. This hot plasma undergo a very rapid expansion. And because of this outward expansion, by Newton's reaction principle, you get a compression of the remaining mass towards the interior. And then, if the compression is enough, the density will increase, the temperature will also increase as a result of compression, and you may reach the condition to trigger the nuclear fusion reaction. And then this compressed sphere will decompress, because by releasing energy, it will explode. So the confinement time is very, very short, because it just depends on the mass of the inertia of the mass that you have compressed. So it's typically of the order of a nanosecond or fraction of nanosecond. Now, this is just what I've just shown here is just the principle. But in order to make this compression, there are two different approaches. One is called direct drive, and the other one is called indirect drive. Indirect drive, as I've just shown before, you use the laser beam to directly irradiate the DT fuel. And the irradiation produce ablation and produce compression and increase of temperature. Indirect drive is a bit different. You have the sphere, your fuel, and you have a cavity. This is called all-round, using a German word. And the laser beams are not focused on the target, but they are focused on the internal walls of these all-rounds. So plasma will be generated at the all-round walls, and this hot plasma will emit X-rays. And in indirect drive, it is the X-rays which compress the target. So why we have different approaches? Well, direct drive is very efficient, but as I will show later, there are problems with uniformity. That is, if the irradiation is not uniform, for instance, if one beam is less powerful than the others, the compression will not be uniform. And if the compression is not uniform, you are not able to reach the conditions which are needed to trigger the nuclear fusion reaction. In the indirect drive, of course, you have a worse efficiency because you lose a big part of the laser energy to create the plasma and to create the X-rays. But the irradiation due to the X-rays is considered to be more uniform than the radiation with the direct laser beam. So actually, the facilities which are operating today, the National Ignition Facility in the United States, the Laser Megajoule in France, the Shenzhen Laser in China, they are working on the scheme of indirect drive. This is the idea. This is the size of the round, which is maybe 1 centimeter by 2 centimeters. And inside you have this pellet, so-called pellet, which is the sphere of the deuterium and tritium ice, which is maybe 2 to 4 millimeters in diameter. And in both cases, either using direct drive or indirect drive, you need to use very big laser. You need to use megajoule laser. And of course, it is not possible to get a megajoule energy by using one laser beam only. You need to use many laser beams. So this is the scheme of the National Ignition Facility, which is operating at the Lawrence Livermore National Laboratory in California. Again, a laboratory which initially was involved in the construction of the hydrogen bomb. And this is the scheme, in principle scheme of the megajoule laser. And actually you see in both NIF and megajoule, the laser beams do not come uniformly around the interaction chamber. They come in two clusters because you need the beam to enter through the holes of the all-round. So in this scheme, the all-round will be vertical with one hole here on the top, one here on the bottom, one hole on the bottom, and the laser beam will be going through the holes to be focused on the walls of the round. Well, just to relax a bit, these are some pictures which were taken during the installation of the National Ignition Facility. And this is the comparison of the size of the National Ignition Facility with some American football field. This is the installation of the interaction chamber, which is 10 meters in diameter. And you have many windows which are needed to insert the laser beam and also to insert the target and to insert the diagnostics, which will tell you if you get or you don't get in nuclear fusion and what are the conditions of the plasma that you create. This is again a picture of the interaction chamber with all the beams which are entering from the bottom and from the top. And this, for the lovers of science fiction, is some image which was taken from the movie Star Trek Into Darkness. And actually some part of this movie was turned around the interaction chamber of the National Ignition Facility in the US. This is a scheme of the megajoule laser, which is very similar to the National Ignition Facility. The main difference between NIF and megajoule is that in NIF you have an interaction chamber and all the laser beams are on one side of the building. In megajoule you have the interaction chamber and you have half of the beam on one side and half of the beam on the other side. And you see that the building is 300 meters long, 60 meters high, 40 meters high, and the region, the hole of the experimental chamber is 60 meters in diameter. and at the middle you have this 10-meter interaction chamber. Just to make a comparison, the height is comparable to St. Basil Cathedral in Moscow, and the height and the length is comparable to the height of Lomonosov Moscow University. And you have 176 laser beams, which are entering this interaction chamber, and in the end, which are entering their focus and entering this very tiny 1 centimeter by 2 centimeters around. And these 176 laser beam provide a total energy in the case of megajoule, which will be when the construction is finished, 1.5 megajoule. So laser megajoule is already operating now, but the number of beams is not 176 for the moment, is less, and the construction to complete the number of beams is still going on. Now, let's look a bit more at the physics of inertial confinement fusion. This is a typical target which is used for inertial confinement fusion. It has 3 layers. The first layer is what is called ablator. This is made by plastic or by glass or by beryllium or by diamond. This, in a way, is the material which is sacrificed. That is, the laser beams focused on the ablator will transform the ablator in plasma. So we do not have interest to directly focus the beam on the DT ice because the DT is our fuel and we want to keep our fuel. Then we have the second layer, which is the DT ice, and then in the middle it is empty, let's say, but actually it's not empty because you will always have some deuterium gas. The radius of this target is of the order of 1 to 2 millimeter, and the mass of deuterium tritium is of the order of milligram. It must be so small because if it is bigger, you have difficulties in controlling the explosion. Right? Why the interaction chamber of NIF and the interaction chamber of megajoule have a 10 meter in diameter? They are so huge. Because indeed, by getting a big interaction chamber, the energy which is released by the nuclear fusion is distributed over a big surface. So the chamber does not get damaged due to the nuclear fusion explosion. But if you get a smaller chamber, or if you get a bigger mass of deuterium and tritium, the explosion will be more violent, the effect on the chamber will be bigger, and the chamber will not survive many shots. So, the present day experiment try to achieve ignition, or which is also called break-even, which means that we try to reach the point at which the energy released by nuclear fusion is equal to the energy which is delivered by the laser and which is used for compression and heating of the target. And by theoretical calculation, you can show that to reach ignition, you have to compress the fuel at 1,000 grams per cubic centimeter. The density of DT ice is 0.5 grams per cubic centimeter. So it means that you have to compress at 4,000 times the density of solid DT ice. You need compression, and then you need to heat the central part of this target to a temperature of 5 to 10 kV in order to start nuclear fusion reaction. And this is called ignition by central hotspot. It's called ignition by central hotspot because you get very high temperature only in the middle, which means that you start the nuclear reaction from this point. And then, of course, the nuclear reaction will release energy, and the energy will heat the surrounding fuel, so you have a sort of nuclear detonation wave, and you will, in the end, try to burn almost all the nuclear fuel. So why we need central hotspot ignition? Why we cannot just compress everything and heat everything to 5-10 kV? Well, the answer is simple. If you have a mass of 1 milligram of deuterium and tritium, it contains 2 times 10 to the 20 ions. And if you want all of these ions to have a temperature of 10 kV, the total thermal energy of the plasma will be 1 megajoule. Now, we have lasers today like megajoule and NIF, which can provide more than 1 megajoule. But only a small part of this megajoule energy goes into the fuel. The biggest part is spent to create the plasma, to ablate the material which produces the compression. So it means that if we have 1 megajoule laser or 2 megajoule laser, and we need to put 1 megajoule of energy into the fuel, we will not be able to do, simply because we miss the energy. So it means that this volume ignition is not achievable. On the contrary, if we compress the target and we only heat up the central part, in principle, we have enough energy to start the nuclear fusion reaction. So, again, the hot spot is formed by compression of the deuterium gas, which is initially contained within the shell. So the ablation, the plasma expansion, produce the implosion of the shell. But as the shell is imploding, the pressure in the middle will increase. And as the pressure in the middle increases, the shell will gradually slow down. And then when the pressure of the central part will be equal to the external pressure, the motion of the shell will end. The shell will stop. This is called stagnation. And it is that as stagnation that we want to reach the condition for ignition. That is, the density of the fuel must be 1,000 grams per cubic centimeter, and the temperature of the hot spot must be of the order of 5 to 10 kV. And because of the way we achieve this condition, you understand that it is an isobaric fuel assembly. The density in the middle is small, the temperature is big. The density around is much bigger, the temperature is smaller, and the pressure is the same everywhere. And now you can see that, if you assume, for instance, that the radius of this hot spot will be 40 micron, the mass of the spot will be something like micrograms, and the energy which is contained within this hot spot will be of the order of 30 kilojoule. So you need only a small fraction of this 1 megajoule energy to be contained into this hot spot. But unfortunately, even this is very, very difficult because the hot spot is heated by the conversion of the kinetic energy of the imploding shell into thermal energy. I mean, initially you have the implosion, you have the shell which is imploding at some high velocity, then it slows down, and when it slows down, its kinetic energy is converted into compression of the fuel and thermal energy of the hot spot. And the conversion energy in this process is very low. It is only 5%. So you have 1 megajoule. or let's say the contrary. You need 30 kilojoule in the hot spot, which means that roughly you need another 30 kilojoule in the fuel. And then if the conversion efficiency is only 5%, it means that you need the laser energy of the order of 1 megajoule. Okay, this is another view graph which I got from Riccardo Betti from the University of Rochester, which is the home of another laser facility, which is the Omega laser facility, which is at the moment the biggest laser facility which is studying direct drive implosion. And again, you see, you have 1 megajoule of energy, 1.8 megajoule here. Most of this energy goes to create the plasma. A small part of this energy of the order of a few percent goes to create the kinetic energy of the imploding shell. Half of this kinetic energy goes in compression and heating of the central spot, and half of this goes on compression of the shell. So, as a conclusion, let's say that you need big laser, you need very big lasers, because unfortunately, we are unable, because of the physics, to put a large fraction of this energy into the compressed and heated fuel. Most of the energy goes in creating the plasma. Now, just some order of magnitude. If the laser energy is 1 megajoule, the duration of the laser on if a megajoule is of the order of 10 nanoseconds, which will be about the implosion time. The radius is of the order of 2 millimeters. And then what we can say, we can calculate the surface of the target, which is 0.5 centimeters square. We can calculate the laser intensity on target, which is the laser intensity, the laser energy divided by the surface and by the duration of the laser pulse, and it turns out to be 3×10⁻⁴ watt per square centimeter. And we can calculate the velocity, the implosion velocity, which is of the order of 2 millimeters divided by 10 nanoseconds, which is 200 kilometers per second. So just 2 comments. First comment, 3 times 10⁻⁴ is not a very big energy. Nowadays, you can have lasers which can reach 10⁻21 watt per square centimeters. But here, you do not want a very big intensity because you want to have a very long duration, because you have to accompany the target during its compression. And because of the big surface, you need a megajoule laser. 10⁻21 watt per square centimeter are reached on very small focal spot, a few microns, and for very short laser time duration. Second comment, we calculate here 200 kilometers per second, which is a very big velocity. In reality, it is even bigger because, of course, at the beginning, the target will need to be accelerated, so it will be slower. At the end, when you approach the stagnation phase, it will slow down. So the peak velocity of implosion will be of the order of 2 times this one. So it will be 400 kilometers per second, which is 400 micron per nanosecond. And there is a final point which is very important, that in order to get the condition of in order to get the compression which you need, 1000 grams per cubic centimeter, you cannot just shine the laser on the target, but you have to make a gentle compression. The compression must be quasi-adiabatic, let's say slow. Slow on the order of 10 nanoseconds, okay, but it must still be gentle. Because if we try to compress too quickly, we will heat the fuel. And when the fuel is heated, it will be much more difficult to compress. and will not be possible to reach 1000 grams per cubic centimeter. So in order to try to get this quasi-adiabatic gentle compression, we need a laser shape. At the beginning, the laser intensity is small, okay, is not zero because it's zero on this graph because it's linear. Let's say it will be 1 to 2 order of magnitude less than the peak. And then you increase, and then you increase, and then you get to the top. By having this pulse shaping, you can hope to achieve a quasi-adiabatic compression. Well, in reality, in current experiment, we are not able to reach a perfectly adiabatic compression. And we introduce this adiabat parameter alpha, which is the ratio of the pressure which will be obtained as a result of a perfect adiabatic compression to the pressure that we really reach. So what I mean, if we have a perfect adiabatic compression, we compress the material, and because of compression, the temperature will increase. But if the compression is not perfectly adiabatic, for the same density, we will get a bigger temperature. So we will get a bigger pressure. So we will get alpha, which is not 1, but which is bigger than 1. Just to give numbers, on the implosion on NIF, what they can get now is alpha, which can be as low as 1.5. Coming back again to the point of to the implosion velocity, a velocity of 400 kilometers per second with the mass of the fuel of the order of 1 milligram provide a kinetic energy of the order of 60 kilojoule. And indeed, this kinetic energy is in principle sufficient to achieve ignition because 30 kilojoule will be spent to compress the fuel, and 30 kilojoule will be spent to heat the hot spot, which is indeed the energy which we need to bring the hot spot temperature of the order of 5 to 10 kV. Well, now, how can you get such a big velocity? How can you get such big kinetic energy? Well, the easiest way is to get a big velocity, okay? You can just increase the velocity or the mass, but you see this formula is quadratic with the velocity and just linear with the mass. So it means that in order to increase the kinetic energy, is more advantageous to increase the velocity. So in order to get high velocity, you decrease the mass. You need a thin shell. Well, unfortunately, these thin shells are very sensitive to the deformation of the target. If you have, for instance, if you have a laser irradiation which is not uniform, where in the point where you have a bigger laser intensity, there will be a bigger velocity. So the target will deformate during the implosion, and the deformation can be big enough to break the shell. And of course, if you break the shell, everything stops. Why the shell can break? Well, actually, this is due to some kind of hydrodynamic instabilities, which is well known, which is the Rayleigh-Taylor instability. Well, probably many of you have done this experience. If you have a glass full of water and you put some paper on the glass, you can turn upside down the glass and the water will not fall. Why? Because actually the pressure, the force which is associated to the pressure of the air is bigger than the gravitational force related to this mass of water. So why, if there is no paper, the water falls down? Well, it is not because of gravity, because pressure is stronger than gravity. It can win gravity in this case. The water falls down because of Rayleigh-Taylor instability. It means that you have a deformation on the surface, which you can represent, for instance, as a sinusoidal deformation. And this deformation will grow in time, will grow exponentially in times. And at a given time, the deformation will be so big that it is of the order of the size of the glass, which means that the water is falling. And basically, this growth rate of this instability depends on the gravitational field, on the wavelength of the perturbation which you are considering, and on the Atwood number, which is the ratio, which is this, the ratio of the difference to the sum of the densities. So you see, if ρ1 is bigger than ρ2, which is the case when you put water above air, this will be positive and gamma will be positive. So it means that you will get exponential growth of the instability. If on the contrary, you put water below and air above, this A will be negative, which means that gamma will be a complex number, which means that instead of exponential, here you will have a sinus or a cosinus, so you will have just a wave. Your perturbation is a small wave on the surface of the glass, and with time, this wave is smoothed, and you go back to the flat surface. So this is the classical growth rate of the gravitational Rayleigh-Taylor instability. In inertial confinement fusion, you have Rayleigh-Taylor instability because you are trying to act, to compress a target. So you are trying to act on a heavy element by using a low density plasma. So it's like here you're trying to bring in place a heavy element, water, by using a low density element, pressure, air, and you are developing the stability. And in inertial confinement fusion is the same. You are trying to compress, to act on a heavy element, the DTIs, by using a very low density medium, the plasma. And then you develop the instabilities. Well, luckily, the growth rate of the Rayleigh-Taylor instability in laser plasmas is not exactly this one, but it is partially stabilized. The exact formula is this one. And this is the scale length of the plasma profile, and this is the ablation velocity. So because you do not have a jump, a sudden jump of density, but you have a plasma profile which is smooth, and because you are removing matter, the growth rate is smaller than the classical growth rate. But still, it is not enough to achieve ignition. Okay, so these are just some simulation showing the effect of Rayleigh-Taylor instability. And the stability is triggered by the defects in laser illumination and by the defects of the target. And this explains the fact that energy must be deposited very, very uniformly. And this explains why megajoule and NIF have been designed by using indirect drive, because people thought that indirect drive is more uniform than direct laser drive. Okay, let's come to recent result. In 2009, 10 years ago, the Livermore laboratory started the so-called National Ignition Campaign. So they just had the National Ignition Facility, which was operational. And they made a series of experiments, which lasted for 3 years, to try to demonstrate ignition. Actually, they wanted to get more than ignition. Okay, ignition means that you get the same number of, the same energy from nuclear fusion reaction as the energy of the laser. Right? So it means that you get nuclear fusion reaction which are producing 5 × 10⁻17 neutrons, which are producing 1.5 megajoule. In reality, they were aiming at much more. They were aiming at getting a gain of 20. So the energy from the fusion reaction should have been 20 times the energy of the laser. Unfortunately, they were not even able to get gain 1. Instead of 5 × 10⁻17 neutron, they only got something like 10 to the 15 neutron. So why there was this failure? Okay, it is a failure because they were not able to achieve nuclear fusion, but it is also, but they got many other interesting results. But still, they were not able to reach ignition. Well, actually, these experiments were designed on the basis of very complex and difficult numerical simulation. And in this numerical simulation, you have many ingredients. You have the question of state of the material at high pressure, because you are trying to compress material, so you have to have a relation between pressure and density and temperature. This is the question of state of the material. You need data on the opacities, which is the absorption and emission coefficient of matter, because you need to know how the laser beam is absorbed in the all-round wall, how it emits, how the all-round plasma emits X-rays, how the X-rays are absorbed by the target. And then there are other problems. There are parametric instabilities which developed in the plasma. This is the so-called stimulated Raman scattering, stimulated Brillouin scattering, which can decouple, that can produce a reflection of a part of the laser light, so they can decouple the laser from the target. They had many other problems. And basically, in the end, the main problem was that they underestimate the impact of Rayleigh-Taylor instability. So this shows indeed that, this shows indeed that achieving ignition is still a scientific challenge. It's not just, there is a technological challenge, but it is also scientific, because we need to get better data on the question of state. We need to get better data on opacities. We need, so that we can make better simulation which are closer to the real behavior of the target. We need to understand better the interaction of the plasma with the laser and so on. And as I say, as I wrote here, you can somewhat predict technological progress. It is much more difficult to predict scientific progress, because you can always find difficulties which were not expected. So achieving ignition is still a scientific challenge, and it is still somewhat unpredictable. And this is true for inertial confinement fusion, and it is also true for the ITER project and for magnetic confinement fusion. Well, so the National Ignition Facility campaign was not successful, but actually after the end of the National Ignition campaign, they continued to do experiments, and they got some more interesting result. again, they were using indirect drive, but instead of using a gentle compression, this quasi-adiabatic compression, they were starting with a bigger laser intensity. So the normal compression is called low foot because they start with a very low intensity, and they were using high foot implosion. And by using this high foot implosion, they were increasing the number of neutrons, but not only that, they were reaching a very interesting point, you know. The energy which was contained in the hotspot was about 4 kilojoules. So you see, we are still far from the about 30 kilojoules which are needed to get ignition. But the nuclear reaction were releasing alpha particles, and the alpha particles, they are confined within the fuel, and the energy contribution from the alpha particle was almost as big as the energy which was initially released, which was initially contained in the hotspot. So we are entering the so-called alpha heating regime. So why is this important? Well, it is important because indeed, if we go back for a second to the principle of the hotspot ignition, we said that we try to start the nuclear fusion reaction in the hotspot, and then we try to get a thermonuclear burn wave which will burn all the remaining fuel. Well, this thermonuclear burn wave is triggered by the alpha particle, okay? The neutron, in the nuclear fusion reaction, you produce neutrons and you produce helium nuclei, alpha particles. The neutron will escape. They are small, they have no electrical charge, so they have a very big penetration in matter. So they escape and you can measure the neutron. But the alpha particles, they are charged, they are big, so they will not escape. Actually, they will deposit their energy in the fuel. And by depositing the energy in the fuel, they will heat up the fuel so that even the fuel can reach the condition for thermonuclear, for starting the thermonuclear fusion reaction. So, getting this alpha particle heating is very important because it brings us closer to ignition. This is just a comparison of the neutron reaction, nuclear neutron production during the national ignition campaign and during the high foot implosion. So you see it was increased by a factor of 10. And why another important point is that the fact that high foot implosion provide better result than normal low foot implosion is a proof that the key problem in order to achieve ignition is really the impact of Rayleigh-Taylor instability. Why? Why do I say that? Well, actually, in principle, the high foot implosion should be worse than the low foot implosion because this is quasi-adiabatic and this is less adiabatic. So it will be more difficult to compress the fuel. But let's look now at the Rayleigh-Taylor instability. You see, when you increase the intensity, you get a longer plasma, so increase this factor here. Oh, sorry. And you also increase the ablation velocity, so you increase this factor here. And these two factors brings to a reduction of the growth rate for the Rayleigh-Taylor instabilities. So these are even more recent results. These are just dating for 2 years ago. They, after making the, you see here you have a different kind of implosion. This is a plastic ablator with low foot implosion, plastic ablator, carbon and hydrogen with high foot implosion. This is using an ablator which is a synthetic diamond. And this is using a synthetic diamond okay, again, this is high foot and low foot, basically. And now you see the latest result is that they got 2 times 10 to the 16 neutrons. And in this implosion, the contribution to the total energy of the spot from alpha heating was 2 times the initial contribution, which is deriving from the slowing down of the imploding shell. Now, 2 times 10 to the 16 means that we are a factor of 50, 2 times, yeah, a factor of 20 far from achieving break-even. So a factor of 20 is not really enormous in physics. So it means that probably in the next few years, we will be able to demonstrate break-even ignition using this approach. Well, anyway, demonstration of scientific feasibility of nuclear fusion, that is demonstration of ignition, will be an enormous scientific achievement. But this will not be very good for the future, because NIF is based on the direct drive, which does not seem compatible with the requirements for future fusion reactors, because the targets are very complicated, because you have massive target, you have a big round made of high Z material, gold, uranium, and so on. So you have a lot of high Z material which is injected in the chamber. And because of the step of conversion from laser light to X-rays, you have an intrinsically low gain. Well, in addition, indirect drive poses political problems because the scheme of indirect drive is somewhat similar on a micrometer scale to the scheme of a hydrogen bomb. So for this reason, the research on indirect drive has been classified for many years. Now it is not unclassified, but still there are many restrictions. So for all these reasons, for future fusion reaction, we will need to forget indirect drive and to go on direct laser drive. Well, the problem is that direct laser drive can have non-uniformities of laser illumination, so it is more sensitive to hydrodynamic instabilities than indirect drive. So how can we solve the problem? Well, actually, the problem can be solved by separating the compression phase and the ignition phase. Central hotspot ignition is very difficult because you try to do 2 things with the same laser. You try to compress the fuel and you try to create very high temperature in the center of the imploded target. But if you can separate this compression and heating phase, then the things become much simpler on paper, of course. And this brings to what is called the advanced ignition scheme, which are basically known as fast ignition and shock ignition. So this is the scheme of fast ignition. I will not spend much time on fast ignition. The idea is that you use a laser beam to compress the fuel, and you do not care about increasing its temperature. You just try to compress. And then when it is compressed, you arrive with another laser beam. In this case, you use a laser beam with short pass duration and very high energy. In the interaction between the laser beam and the target, you create a lot of very hot electrons, relativistic electrons. They penetrate in the compressed target and they produce the increase of temperature which is needed to start the nuclear fusion reaction. So in a way, this is like a normal gasoline, a normal engine. You compress and then you have ignition. For comparison, the central hotspot ignition will be more like a diesel engine in which you just compress and then the fuel just ignites because you have reached a big temperature because of compression. So fast ignition is a very beautiful idea, but the point is that in order to do fast ignition, you would require a laser which provides at least 100 kilojoule in 10 picosecond in a spot of 10 micron. And this one is beyond the present day laser technology. The biggest short pass laser that we have today can deliver energy of about 1 kilojoule in about 10 picosecond, maybe in a spot which is a bit bigger than 10 micron. Moving from 1 kilojoule to 100 kilojoule is beyond what we can do today and what we will be able to do probably in the next 10 years. So it is, in a way, we don't have the laser tool which is adapted to study fast ignition. So we go to shock ignition. Shock ignition is closer to conventional ignition. This is the laser pulse for quasi-adiabatic compression on a logarithmic scale now. And now we have the same one, but maybe at a lower intensity, because here in the normal approach, we try to reach very high implosion velocity, 400 kilometers per second, because we try to hit the target. And the hitting of the target comes from the conversion of this kinetic energy. Here in shock ignition, we implode the target at much lower implosion velocity because we just want to compress. And once the material is compressed, again, we use another laser beam, which is very high intensity and shorter, but is not so much high intensity and so short as in fast ignition. Typically, here we are at a few times 10 to the 14 watt per square centimeter for compression. And for ignition, we will use a laser intensity of 10 to the 16 watt per square centimeter. And the pass duration will be a few hundred picoseconds. So this laser pulse will create a very strong shock, which will move inwards, will reach the center of the target, and the shock convergence will hit the target to temperatures which are enough to achieve the ignition. So basically, these are the advantages of shock ignition. In shock ignition, you do not need to create the spot with the main compression beam. So you do not need high implosion velocity. You implode a more massive and thicker shell. And because the shell is thicker, even if you develop hadron instabilities, they will not be enough to break the shell. Well, and also the final fuel assembly will not be isobaric, but it will be non-isobaric, which means that the center will have a bigger density and bigger temperature as compared to the normal spot, which means that you can, in principle, get bigger gains. So these are just some simulation of a imploding target. Well, this is a so-called hyper-target. Without the final spike, you see the development of the Rayleigh-Taylor instability, and the nuclear fusion yield, here it will be 0. And this is with the final implosion, with the final ignition spike. The development of the Rayleigh-Taylor instability is still there, but it is smaller. And in this case, you can get energy from the nuclear fusion reaction. Well, shock ignition experiments are now undergoing. There are some experiments, for instance, which have been done on the Omega laser facility. They have compared a normal laser pulse with a laser pulse which is like shock ignition. Unfortunately, the Omega laser facility is not a megajoule laser, and they only have about 30 kilojoule of laser energy. But these are just experiments which can show the principle. And indeed, these are the Newton rate without the final spike and with the final spike. And you see that the implosion was, the implosion outcome was much better, of course, with the spike. Well, the main difference between shock ignition and fast ignition is that the laser pulse which is needed for shock ignition can in principle be done using present-day laser technology, which means that in principle NIF, megajoule, Shenguan can be adapted to produce a spike of 10 to the 16 watt per square centimeter in 300 picoseconds. So shock ignition can be tested in the next few years. But there are many, of course, there are many problems because this is a new field. We don't know much about the laser plasma interaction at 10 to the 16 watt per square centimeters, and we need to do experiments in order to understand what's going on. For instance, I was speaking before about parametric instabilities like stimulated Raman scattering, stimulated Brillouin scattering, and there is also a third one which is called the two-plasmon decay. These instabilities can reflect a large part of the laser beam. So you come with 1 megajoule laser energy, but if they reflect 50%, you will not be able to make ignition. So you must understand how they developed and how it is possible to suppress their development. And also there is another point. These instabilities tend to create a lot of hot electrons. And these hot electrons can be dangerous for nuclear fusion, because if you have hot electrons, they can penetrate deep into the target and then can increase the temperature and they can make compression more difficult. Well, this is at least what is true for central ignition. Now, in shock ignition can be different. Okay, this is a view graph which I got by Sergei Guskov, which is a professor and researcher at the Lebedev Institute. And together with other people, he has developed the theory of a shock wave which is driven by hot electrons. So in normal laser plasma interaction, the laser is absorbed at some critical density, and then the energy is transported inward by the thermal electrons, producing a shock wave. And then you can deduce a scaling of the pressure, which is the intensity to the 2/3 times this value of the critical density to the 1/3. If the shock is produced by the electron beams, you end up, by the hot electrons, you end up with a similar scaling, but instead of getting the critical density here, you get the solid density, which means that the pressure can be much bigger. Well, so this can be very good for shock ignition, but we have to try to make experiment to understand what is really going on. Once we have done this one, there is an additional problem. The laser problem, the problem is that the lasers, NIF, megajoule, Shenguan, can produce the required pulse shape, but they have not been designed for direct drive. They've been designed for indirect drive. So the laser beam do not come uniformly around the target, they come in the top and in the bottom. So if I want to try to get a uniform implosion, I have to repoint and to defocus the laser beam to try to get a uniform illumination on the sphere. And this is what is called polar direct drive. And again, this is something which works on paper, but for which we have to make experiment to see if it really works. So I come to the conclusion. There's still a lot of interesting physics concerning nuclear fusion and concerning shock ignition in particular. And the physics must be understood and mastered, and this can be done on smaller laser facilities. Now there are a number of laser facilities like Felix, Vulcan, Pulse, Orion, Omega, Gecko in Japan, where we do not have the needed energy to demonstrate ignition, but we can have the intensity to study the physics. And then, once we understand the physics, we can try to do demonstration of shock ignition on these machines which have been built for indirect drive, going through indirect drive. And in conclusion, I think that this is an exciting field for researchers in physics for young people at the beginning of their career. So thanks a lot for your attention.